All right, let's go with few exercises and try to finish up the first chapter. Okay, so in the first video we did introduction, and the second video covered the point number 2 to point number 6. So today this video will just do like about 4 exercises, and then we stop. We finish the first chapter. Okay, so let's go with the first exercise. Exercise number 1. We we want to determine the elongation. Elongation means the increment of the length of the steel top. The total length is 50 meters, and the section is 10 by 0.5 millimeters. Okay, and this it is subjective to tension, a force of 10 Newton, and the modulus of elasticity is 2.5 megapascal. So here is the summary of the exercise. The length L, the section S, the force acting on the structure is F, which is 10 Newton. Okay, so we are going to apply just the Hooke's law and estimate the variation in the length. Okay, elongation. What is the variation, the increment in the length? That's what we want. So the Hooke law is given by this formula, and we explained this, I think, in the previous video. You can see it here. This is the deformation. It means the strain. Okay, strain and stress is here. The strain is just the variation in the length divided by the original length, and the stress is force divided by this area, the section. A is for the section. Okay, so the relationship between stress and strain in this elastic zone is what we have here. Stress can be obtained from Young modulus and strain. Okay, this is the formula here. So from this equation number 1, we can replace these two. This is formula of strain, delta L divided by L. Okay, and this is what we are looking for. This is what we want to calculate, the delta L. The sigma F divided by the section S. We have everything here, I think. We have L, which is, I think, 50 meters. And we have sigma, we have F, 10 Newton. S is the section, which is 10 by 0.5 millimeters. So you just have to be careful about the unit used. Okay, I will put these equations here. So by replacing this, the strain in this equation, number 1, and the sigma replaced by F bar divided by S in here, we can easily obtain the value of delta L like this. Okay, so this, using this formula, you can just use the value and obtain the delta L easily. But remember, you have to convert, for example, this one in from megapascal to pascal. That means multiplying it by this 10 power 6. Okay, the section here is, you can keep it in millimeter if you want the variation of the length in millimeter. So the 50 meters here should be converted in millimeter. So multiply by 1000 power 10 power 3. Okay, so L is this, F in Newton, 10 Newton, and the section 10 by 0.5 in millimeter, because the length here also is in millimeter. In that case, you can obtain the variation in the length in millimeter. So it about 5.10 power minus 7 millimeter. It's very, very small. It's difficult to notice this with naked eye. Okay. So this is exercise number 1. Let's go to exercise number 2. Exercise number 2 is about this. We have a bar, this let's say steel bar, or I don't know, any other material. So here we don't have any force acting on the bar. The bar is subjective to its own self-weight only. And the length is L, okay, or the height if you want. And the density, the unit weight, if you want, is the mass unit weight of this element is rho here. And the bar is suspended like this, and it will be subjective to its own weight. The force acting on it will be the weight, the self-weight. Okay, so we want to determine the variation in the length, elongation, under the effect of the self-weight. Okay, and we have the Young modulus E. So we will consider here small element, this small element, elementary element here, and we study this element. The thing is, at any point you are in this bar, for example, if you are in this element, okay, the weight of the bar acting on this element is the weight of this part under this element, under this point. So you just choose anywhere, an element anywhere in this bar, and consider this element as the element of study. And the length of the element is dy, like this, and the element is at position of y, the coordinate y, from 0, because we have, if we have the, we start here at 0, so we are going from 0 to L. L is the limit, total length. Okay, so at any coordinate, we can determine any coordinate y. Here you can choose a elementary element. Here, parent, same. Okay, this small element, we can study this and determine the length variation of this small element. After that, we can just do a integrate to obtain the total variation in the length. That is not complicated, I think. So the total length, the volumic mass, the Young modulus E. So the weight, let's consider here Fy is the weight of this element. And to have the stress, we have to divide the force acting on the element by the section S. Okay, so this is the stress, F divided by S. So according to the Hooke's law, this element dy, we can obtain this formula. This is sigma. Okay, sigma, which is Fy divided by S here, equal E, Young modulus, elastic modulus, delta dy divided by dy. So dy here is this, the length, the small, the elementary length we have considered. Okay, and delta dy is the change in length of this small element, the elongation of this small element. Okay, so that is, so means delta dy divided by dy is the strain here. The variation in the length divided by the total length, the original length, which is here dy. So the F here, the force acting, as I told you, it will be just be the weight of the bar. So if we are at this position, the weight of this, the part of this bar under this position will be acting on this element. So we have to calculate the weight. The weight, you just take the mass multiplied by G. Okay, G maybe 9.81. That is for the gravity. Okay, so unit mass, volumic mass, the mass unit weight multiplied by the volume, because S, the section multiplied by Y, because we are trying to calculate the weight of this part, and the height of this part is Y here. And the Y multiplied by the section we cannot see it here. Section will be like this part. Okay, if we had it in 3 dimensions, but unfortunately we cannot see the section here in this figure. Okay, but the height, this length multiplied by the section will give you the volume. Okay, S by multiplied by Y is the volume. The volume multiplied by the unit weight, the mass unit weight, will give you the mass. Okay, in kilogram, for example, and the mass multiplied by G, the gravity, will give you the weight, and that weight is the force acting on this small element, the force, the weight of this part. Okay, so you can do F. Later we will replace the F by all this. Okay, so if we do that, replacing this F by all this, we obtain something like this, and we can obtain the small change, the delta gy. It means the variation in length of this delta y dy. Okay, delta dy, this is what we want, so we can obtain it from this equation. Okay, and replace this fy by all this. And then, as you can see, we can drop the s, the section here. You can just simplify the equation. Then we can obtain the total variation of the length by integrating this integration, okay, along this bar from 0 until the end here. It means L. The total length is L, right? So here is 0. If you reach the maximum is L. So from 0, it will be from 0 to L. Okay, so this rho is a constant. G is a constant. E, the Young modulus, is a constant. So we can send this out. Okay, we will have only y dy, which is easy to integrate. Okay, the primitive of this. So we can send this constant out and integrate from 0 to L y dy. That is very easy. It will be just 0.5 or 1 over 2 y square power 2. Okay, then we can obtain this. So it means the total variation in the length will be obtained by this. Because as you can see, it doesn't depend on the section at all. It depends just on the unit weight, massic unit weight, the gravity, the Young modulus, and the length L here. Okay. Okay, let's go for the exercise number 3, which is let me go directly to the summary of this exercise, because we have two prismatic bar rigidly fixed together, and these are subjected to a load of 60 kilonewton. The upper part is made of steel with density of steel 78 kilonewton per cubic meter. The length of this upper part is 10 meters. Section 60 by 10 power minus 4 square meter. And the lowest part of the bar is in bronze. And the density is 80 kilonewton per cubic meter. The length is 6 meters. And here we have the section of 50 multiplied by 10 power minus 4 square meter. So the Young modulus, elastic modulus for this is still in French. Okay. So the Young modulus, as you can see, this is power 9. Okay. 10 power 9. It's not like this. Here is a mistake. Like here also, same. Okay. You have to consider it. Means 21 point multiplied by 10 power 9. I hope you understand what I mean. Okay. So we want to calculate the maximum stress in each of these two bars. Okay. So we have here the load. This is summary. The load, the upper part. Actually, it's better in this way. The upper section, we have these two bars here, and we have the load, 60 kilonewton here. This one is in steel material, and the density 78 kilonewton per cubic meter. The length 10 meters. The section of this bar, the bronze, this second part is in bronze. The length is 6, and we have the section and the unit weight. Okay, so the Young modulus now. So as I said, this is 10 power 9. This is also 10 power 9. Okay, maybe we don't have time to correct it. Let go. And we want to calculate the maximum stress in each of these sections. So the thing is here, you need to know where the maximum stress should be in each of these bar, steel bar and bronze bar. At which position you have the maximum stress. Let's take in the case of the bronze, this material, the maximum stress will be at this section B prime. The reason for that is because this is subjected to its own weight and also subjected to this force Q of 60 kilonewton. So if you are at any point, any position, the force acting at that position is this force plus the weight under this section, exactly like the previous exercise. So it means here, this position is where the stress is maximum in this bronze material. For the steel material, as you may guess, it will be here. Okay, so let's decide like the PB is the weight of the bronze, B for bronze, and PA is for the steel. Okay, PB, the unit weight of the bronze multiplied by section and the length, means by the volume, we can get the weight of this bronze part. For the steel part, it's same, the unit weight multiplied by the volume. Okay, 10, this is the length and the section, and we obtain this 4.68 kilonewton as the total weight of this. So this bar, this bronze bar, will be subjected to this force and its own unit weight. So in that case, the maximum stress here, let's name it sigma B, will be this force divided by the section. The force is Q plus PB. PB is the weight of this bronze part, this 2.4 kilonewton. So plus this 60 kilonewton. Okay, and the section is the section of the bronze. So it will be just like this, very simple. Okay, 60 plus 2.4 divided by this section of the bronze. Okay, you should not divide by the section of the steel, because you want the stress in the bronze, not the stress in the steel at this position. So for the steel material, this box, this bar, it will be here. So the forces acting will be this 60 plus the total unit weight of the bronze and the total unit weight of the steel. So it will be here, the maximum will be here. This is because we are asked to calculate the maximum, okay? So we can also try, for example, to search the stress here at the middle here or here. At any position, you can try by using just the weight of the material under that position and this force combined to be the force causing the stress by dividing by the section. Okay, so we have here three forces. This 60 kilonewton, the weight of the bronze plus the weight of the steel. So it will be this divided by the section of the steel. This. Okay, and we obtain this. This is end of this exercise number 3. And let's go for the exercise number 4. This time we consider this beam, a beam that is loaded by this force F, the uniform force F, this side and this side. And the geometry of this beam is like the thickness is constant. The thickness is, we cannot see it in this because this is a section. So it will be in 3D. It will go like this. Okay. And the height at this position is A, as you can see, A. The height of this at this position is B. So they are not same. And the length L here. Okay, this is what we have. So we want to calculate the shortening, how much this beam will become short because it being compressed by the two sides, this side and this side. Both of them are being compressed, both sides. So the length L will be shorter, okay, under this force. How much it will be? So we have the length, the thickness E, and the elastic modulus E. Okay, so what we can do is we take this small element, exactly like exercise number 2. Okay, and we study this small element, small variation, and see what will happen. Okay, so that means this element, now we are going from here, the origin here, to until the end, which means L, from 0 to L. and this element is limited by x, this x from here to dx, dx. So this is the thickness of this small element. So this is made large to allow people to see, but it will be like very close. This section and this section will be very close so that they can be considered as same. Okay, so same, we can apply the Hooke law here, and we can obtain the delta dx, which means the variation in length of the dx. Okay, variation of in length of dx obtained by the force, the elastic modulus of, and the section x. Okay, these two sections can be considered as same. I keep this formula here. So the two sections here at position x and position then dx, x plus dx, they can be considered as same since these two sections will be very close. Okay, so we can say that sx means the section here is this y. Y is the height of this section. Okay, y. Okay, multiply by the thickness means e. Thickness cannot be seen here. Okay, if we had it in 3 dimension, we can see the thickness here. So the section can be calculated by using the y by e. And there is simple relationship, high school relationship, that you can help us here to get to the y. It's like when you take this height minus this height, this is like theorem of Thales, and you divide by the distance between these two positions, means L in this time. This height minus this height means A. This height is A minus this is B. Okay, and divided by the distance between these two. In this case, it is L. We can say it is equal to this y minus b divided by distance between these two sections, which is this distance is L, the total distance, minus x, right? X, this is x. From x is going from the origin here to here. So if we do L, the total distance, minus x, we obtain exactly this distance. So this is what here is here. So from this, we can just obtain our y here, the y here, and we obtain like this. And if you do development, fit multiplying here, you can get this. And by multiplying L here by A, you can have the same denominator like this, and you can obtain this. Okay, so by using this y, we can just replace it here, multiply it by E to obtain the S, and we can replace this S by in this equation. Okay, so S will be this E divided by L multiplied by all this. This is our S, and we will take this S and replace it here. All this expression of S, we will take it and replace it here, and we will get S is here. By doing that, we will obtain this dx. Delta dx will be equal to this. Let me just bring it back here. This is S. and we bring it here. Okay, now we're good to go. So this value of S, this expression, this formula of S will be replaced in this equation. So we can have our variation in the length. Okay, and it will be like this. By replacing, we can have delta dx. Okay, just replacing this x. The dx here it's same. So the thing is, when you divide this, it will be reversed. This L will come up. This is a dividing fraction with another fraction. Okay, so we obtain something like this for the delta dx, means the length variation of this small element. And then we can just integration of this, all this, to obtain the total elongation, the total length variation. And we have from 0 to L, from here until here will be L, okay, dx. So we can bring out everything that is constant. F is a constant, L is a constant, E is a constant, this small e is a constant. We will have this. So it will be just this, we need integration of from 0 to L of this part. So how we do that? As you can see here, it's a little bit complex to find this here. So I will keep the equation here. We need integration of this. So we need to bring like change variable. This is just high school mathematics now. Okay, solving this equation, this integration is just a mathematics of high school mathematics. Okay, so we make a change or in variable changing. We will consider this, all this as u. Okay, u here. So if we do that as u, and derivation, we derive u, du will be, if this is constant, if you derive it, it will be 0. If you derive this, it will be dx. Okay, so dx. So we have, from this, you can obtain dx here, right? It will be du divided by b minus b, by b minus a. Okay, obtain dx. And this dx will be replaced here. This one will be replaced by the value of dx here. It means du divided by b minus a will be replaced here. And for this one, this is already u here. Just replace it by u. All this will be replaced by u. Okay. So we have something like this. Du divided by b minus a. This is dx from here. Dx means du divided by b minus a. This is here. And multiply by u, because all this is u, as we assumed here. This is our assumption from the beginning. Okay. Then you know that this is a constant again. So as it is a constant, we can send it out here. Okay. Then you know that du divided by u, this is just the logarithmic function, as the primitive of x prime divided by x is ln of x. The logarithmic function, high school. Okay. So now we need to know, for example, if x is going from 0 to L, how about u? if x is 0, replace x by 0 here, you will have u will be al. However, if x is l, replace x by l here, you will have al plus b by l minus a by l. Minus a by l here will be simplified by this al here. And you will have u is equal bl. Okay. Okay. So this is what I was explaining. If x is 0, u will be al. Replace x by 0 here, you will see. If x is l, then u will be equal to bl. Replace x by l here, you will see. Okay. Then our integration will be bl here, and because x is going from 0 to l. This is really high school stuff. Okay. So we can have in total delta L will be this, because here it will be ln of BL minus ln of AL. And as a property of one of the property of the logarithmic function, ln function is if you have ln of A minus ln of B, you can say that it is ln of B bar B, A divided by B. Ln of A minus ln of B can be said ln of A divided by B. So here, if you divide BL by AL, you can simplify, drop the L. It will be B divided by A. So ln of B divided by A. Okay, this is just one property of ln. So you have the total variation of the length as here. So it means it depends on the force, on the F. It will depend on the L. It will depend on the Young modulus, of course. It will depend on the thickness, E, which we cannot see here, this section. And the height here, A here, and B here. That's all. Okay. Thank you very much for your time, and see you soon.